Moore's law states that the average computing power of any device doubles about every 2 years. It sounds crazy. How can innovation maintain such a fast pace forever? Well, the bad news is, some people think it can't. We've basically reached the limit of how small and dense we can make our transistors. Moore's law might be coming to an end. The good news is, quantum computers might help us get back on track. Quantum computers can do things that normal computers could never dream of feasibly by exploiting the power of parallel universes. If that sounds insane, it's because it is. In this video, I'm going to explain how quantum computers handle information differently than regular computers, and then explain one theoretical algorithm taking advantage of quantum architecture. A quantum bit, or a qubit, is a bit that can be on and off at the same time, which I'm sure everyone's heard of, and I know it doesn't help understand what they are or how they work. So for the first part of this video, I just want to clear up what a bit that can be on and off at once really means. So what is a bit? Well, a bit is just a simple piece of information, a 1 or a 0. A qubit could be a 1 or a 0, but thanks to quantum entanglement, it sometimes hasn't made up its mind and is sometimes somewhere in between. Qubits are usually represented like this, where alpha and beta are some measure of probability that we'd find our bit in one of the two states. More specifically, alpha and beta are complex numbers such that their magnitudes equal one of our two measurement probabilities. Since alpha and beta are probabilities, the magnitude of alpha squared plus the magnitude of beta squared must always equal 1. This means we can rewrite this like this. Hey, these are polar coordinates, which means we can represent a single qubit as a point on the unit sphere. This is an on qubit, and this is an off qubit. Here's a qubit that's somewhere in between. Here's another qubit that's somewhere in between, but the phase is slightly different. Unlike classical bits, which only have one unary operator, qubits can have infinite. All of them correspond to rotating the unit sphere. The most common one is the Hadamard transformation, which ports a normal bit into superposition. Here's what it looks like. Unfortunately, in systems with more than one qubit, we can't visualize them on this sphere. Take, for example, a system with 3 qubits. The system would need complex numbers to represent the probabilities for the 000 state, the 001 state, the 010 state, etc., all adding to 1. That's a lot more than 3. It's 8, in case you can't count. The good news is, this means if we have n qubits, we can store 2 to the power n meaningful pieces of information. The only problem is we can't measure these systems directly. Anytime we try and ask a quantum system, hey, what state are you in? It will collapse down into a single answer. So how would we use quantum bits to actually do computing? One of the craziest algorithms quantum computers can use is called Grover's algorithm. Say you have n choices for something, only one of which is the right answer, and you want to search through the list to get it. It's easy to see that a computer and a human would do this in linear time, big O of n, and it's hard to believe, but quantum computers can actually do this faster. Say we have n options, each one can be assigned a unique index from 0 to n. Let's use binary for the indices, since we are computer scientists. Now imagine a function that recognizes a correct example. F of x is 1 when we have a solution and 0 when we don't. Pretty easy, right? But what if we took one possible index registry and we applied the Hadamard transformation to it? What if effectively our index registry was equally every combination of index registries simultaneously? What would happen if we plugged this into our f of x? Here's the algorithm. 1. Start out with a set of qubits, all initialized to 0. 2. Put our whole system in superposition so that every combination of bits is equally likely to be observed. 3. Feed our qubits into a circuit that looks like this so that the amplitude of the correct solution is slightly marked. 4. Flip the phase of all the states so that a high amplitude corresponds to an increased likelihood that we have the correct solution. And 5. Repeat this process a few times. And at the end, when we measure our system, we'll have the correct answer about 99% of the time. For n items in our search space, it turns out that we only need to perform this the square root of n times to get a good answer, a huge speed up over classical algorithms. This isn't a joke or a trick, and it isn't some theoretical paradox that could be used. This happens and has been tested. Quantum computers are that bizarre. But if it keeps Moore's law alive, I guess we just need to learn to accept its insanity.